Let's talk about Riemann sums. Riemann sums is a way to approximate the area under a curve, and ultimately we can do that with a definite integral. So it's really a way of approximating a definite integral. And as we learn about Riemann sums and we actually do infinite number of rectangles, we'll see that it actually leads to a standard definite integral. And then we'll do a definite integral on this problem because I picked a nice easy one here to compare how accurate these Riemann sums are. And we'll also see that if we increase the number of rectangles, in the case of the left-hand and right-hand rule, that will get more and more accurate, ultimately with an infinite number of them being 100% accurate. And really, that's how we define the definite integral. So let's start with this easy function. I'm picking this function because we can really find the area under this curve exactly, and then we'll compare our approximate methods and see how close they get. So I've listed the 4 methods here. We're going to do all 4 on this, this picture here. But the one thing I'm going to do a little differently than maybe traditionally is done is I'm not going to start with a rectangle with a width of 1. This way the midpoint will fit in nicely, and it's more typical on an AP exam, which is what this course is focusing on, where the midpoint would probably be an actual data value rather than like a 0.5. It's not that it's impossible to do, but it's typically not. So, and that's one of the first things we do when we have Riemann sums is we decide how many subdivisions there are, and of course where we're going from and to. So in this problem, we're going to do from 0 to 6. And when we go to the formulas, which I'm going to actually avoid for a while, we do talk about A to B. A being the beginning and B being the end. So what we're really trying to do is find this area under here, right? All under here. So we're trying to find this area. We're not going to be able to exactly find it, not using a Riemann sums. But we'll get a very rough, a very good estimate, I should say. It's going to be rough in some cases, better in others, but it'll be a good estimation. And we want it between A and B, so we want to get that area. So the shape that I just highlighted for you a second ago is, of course, an irregular shape, and you can't just find the area of it. So we're going to use regular shapes, in this case rectangles for the left-hand rule. Okay, we're going to use rectangles to find an approximate area. Okay, now we're going to actually make 3 rectangles here. You may make 6, and that would be much more accurate. And we define that by the number of subdivisions, so which is called n. And problems that you get on the AP exam will typically indicate this for you. So for example, they may say find the area between x equals 0 and 6 with n equals 3, or they may just say with 3 subdivisions. And what that means is we're going to get 3 rectangles, right? So we're going to get a rectangle here. I'm just going to draw a rough rectangle. This is not the actual thing going on here, right? But I'm going to get a rectangle, rectangle, and a rectangle. I'm just kind of randomly drawing rectangles here. So we're going to get 3 rectangles because this says to make 3 rectangles. And what happens is that will define where we're going to make the left and right side of my rectangle. So we're going from A to B, but A is 0 and B is 6. So that means there are a distance of 6 along the x-axis, and because n equals 3, we're going to divide 6 by 3. 6 by 3. And we're going to get 2. So 2 basically means a width of 2. Okay? So I know the bottom of my rectangle is going to be 2. So from here to here will be my first rectangle. Okay? And then from 2 to 4, my second, and 4 to 6, my third one. Okay, so let's focus on left-hand rule. So left-hand rule means left, meaning when we draw our rectangle, see, we're going to draw up here, and we're going to draw up here. But what we're going to do is left-hand rule, this L here says the left side will drive the height of your rectangle. So we go up the left side of my rectangle until I hit the function. Okay, so the function is this red line here, which is square root of x plus 1. And we're going to go, and we stop as soon as we hit the function. Once we do that, we go straight across, because that's the height of my rectangle, and then we come back down the right side. So that's the left-hand rule. Notice I went across 2, again, because they told me the subdivisions were 3. If this had been 6, if they wanted 6 subdivisions, then I would have made a rectangle with width 1, from 0 to 1, and then another one from 1 to 2, and another one from 2 to 3, etc., etc. Okay, I got to make my second one. That was my first rectangle. I make my second rectangle, which is going to be from here to here, right? There's the base of the rectangle. But I'm going to go up the left side because it's the left-hand rule. So I go up the left side until I hit the function. I stop, and I go straight across, and then I come down the right side. Okay? Now, I wrote a little note here. Is this an over or underestimation? An over-underestimation. So I think you can kind of see that we're missing a lot of area, right? So this area is not getting covered, right? We're going to get the area inside these rectangles. It's going to ignore this blue area. So for this red function here, this radical x plus 1 function, it's an increasing function, right? It's increasing as we move to the right. So if we do left-hand rule, that's always going to be an underestimation, okay? So for this one, it's going to be an underestimation. When I do right-hand rule, you'll see that it will be an overestimation. But that's because the function is increasing over the entire interval from A to B. Okay, my last rectangle is from 4 to 6. From 4 to 6. I'm going to go up the left-hand side. I go up all the way till I hit the function. There I hit the function. I stop, and I come down like this. Okay, and there's my 3 rectangles. And it's not going to be a great approximation. It's going to be an underestimation. Had n been larger, right? So if this had been 6, if that's 6, then it's more accurate, right? So this would be more accurate with 6. We don't have 6, we have 3, so it's not going to be less accurate. Okay, so what we're going to do is we're going to add the areas up. Okay, and this first area is easy. It's got a width of 2 and a height of 1. Okay, why? Because I'm plugging in 0. This is the left-hand side of my rectangle, see? I'm plugging 0 in here, right? So when you put the square root of 0 plus 1 is 1. So the area of this rectangle is 2, and I often like to put it in a circle inside the rectangle. You don't have to. Okay, it's 1 by 2. All right, this one, not so easy, right? This one has a width of 2, so I know it's going to be times 2. But when I plug in this number, that's the left-hand side, because remember, the height here, right, that point has an x and y coordinate, right? That point has an x and y coordinate. And of course, that point, let's get rid of this. That point has a coordinate of 2, comma, something, right? Well, what is this something? Well, that's what happens when you put 2 in here, right? So you plug in 2. So it's the square root of 2 plus 1. It's not a nice, easy number. And so I'm going to leave it as square root of 2 plus 1. Squeeze it in there. And that's my y value, okay? So the area of this thing is the base, 2, times the height, which is the function's y value, or in this case, the f value, the height of the function. And you get that by plugging in the number on the x-axis, the x value, on the left side of the rectangle. Of course, this was the right-hand rule we do on the right side. So this area is actually 2 times the y value, the height, at the left-hand side, which is radical 2 plus 1. Okay? Now, I'm not going to circle that, actually, because it's a little cumbersome, but okay, yes, I am. Change my mind. A little busy, but it's okay. The third rectangle goes starts here along the left side where x equals 4, and it goes all the way up to here, and that's, of course, a height of 3, right? So if you plug in 4 in here, you get square root of 2, square root of 4, is 2, plus 1 is 3. So this is going to be 3 times 2. Some people leave it every single time like this, right? They just do this. Okay, 3 times 2, which is 6, of course, and this you could have done 1 times 2. Doesn't really matter. I mean, the answers are pretty obvious here. 2, a little complicated number here, and 6, right? All right, so we're not actually doing a definite integral, and you may not have even started with definite integrals yet, but I'm going to draw one anyway, because in the AP exam, that's typically how they ask it, or often how they ask it, and often how you want to write it. So what we're going to say is the area under the curve, that's the integral, from 0 to 6, of my function, so this is the function f of x, dx, okay? You could actually put the function in there too if you wanted to, but this is typically how we do it, is approximately, right? That's really important that this is an approximate area. You can clearly see it's approximate because we're doing an underestimation. We're losing a lot of stuff, okay? So, and we're going to actually solve this definite integral in about 3 seconds when I'm done with this, and we're going to get the real answer and see how far off it is, okay? But what you're doing is you're approximating this rather than using the rules of indefinite integrals, because a lot of times we're going to be dealing with a table of data. So I'm going to give you a table of points so you don't know the exact value because you don't have a perfect model for the function. But in this one we do, and I picked that on purpose. So the area of this is the area of the 3 rectangles, right? So it's going to be 2. That's the area of the first rectangle. You don't have to do what I'm doing here on an exam. I'm just showing you that. Plus the area of the second rectangle. And this is a little more complicated, right? So it's 2 radical 2 plus 1. And that's the area of the second rectangle, right? The second rectangle. Plus the area of the third rectangle. And that is 6, right? Pretty easy. Okay. And we're going to get a number and approximate it here. Okay. And we'll do that in a second. So the total is 12.8284. So we're going to put 828. Remember, you want at least 3 decimal places on the AP exam. And you can truncate around. I usually round because it's more instinctual. Okay. Now, the actual area, and if you haven't done definite integrals, you'll just have to trust me, but it's pretty straightforward. And we're going to actually write the function here of the square root of x plus 1 with respect to x. Okay. Real quick, this is x to the 1/2 power, so it's x to the 3/2 power, right? Over 3/2, but that's really just 2 over 3, plus x. Okay, the integration of 1 is x. So, and then the evaluation symbol from 0 to 6. I usually pick a nice number like 9. I didn't this time, so I'm going to use a calculator here. And all that means is we're going to plug in 6, and we're going to get a number, and then we're going to plug in 0, which, by the way, gives me 0, so I don't have to really worry about it. So it's going to be minus 0. And that will give me the final answer. So really, it's whatever you get when you plug in 6, okay? So I'm going to go over to a calculator. I'm going to square root 6, then cube it. So I'm going to go square root 6, then cube it. Try that on your calculator while I'm doing this. Times 2 divided by 3. And then, of course, add 6, because you're adding plus x, right? So add 6. And if you do that on your calculator, you're going to get, I hope, 15.798. 15.798, yeah. And as I expected, right? As I expected, this is, of course, bigger than this. And I expect that because of all this sort of lost area for this bad, not bad, but not great approximation, right? So I lost all this area under here. It's not perfect, but you get the idea. So all that area is gone. That's why the actual answer is, you know, a little bit higher than 12.8. Had I done 6 rectangles, or if n equals 6, right? Like I said over here, if n is equal to 6, then you're going to get a much better approximation here with the left-hand rule. Okay, let's go and do the right-hand rule. And I am actually going to leave the old one here because I do want you to see the comparison between the two and how there's a pattern, and then that'll lead us to something else later on. So, but I'll pick a different color, so I'll use, I think, green. And let's do the right-hand rule, okay? So we'll do the right-hand rule. So to do the right-hand rule, it's the same thing. I'm going to make 3 rectangles just like you see here, except that I'm going to go up the right side. So my first rectangle, again, because n is equal to 3, still this hasn't changed, is going to be 2 wide, okay? And I'm going to go up the right side, and I keep going until I hit the function. Okay, so there it is. I hit the function there. And then I go left, because remember, I'm trying to finish this whole rectangle here. See, this is a rectangle. I've got to finish the rectangle. So I'm going to go left from that point, and that's my first rectangle. And if you figured out that this one and this one are the same, you're right, obviously. And you also probably figured out we're going to have an overestimation when we do the green because all of this is too much area. And you may have figured out that a great way to approximate this is to do the left-hand rule and the right-hand rule and average the two. And that is also correct. Okay, let's go up the second one. So the second rectangle, which has a base down here of 2, right, from 2 to 4, we're going to go up the 4 side, go all the way to the top, and go straight across and back down. And for my last rectangle, again, 2 across, I'm going to go up the right-hand side. I'm doing the right-hand rule until I hit the function. And we're going to come over here. Whoops, it's a little too sloppy even for approximation here. And straight down. Okay, now I'm going to write the areas in green. So this area in the first rectangle is exactly the same as the red rectangle, right? The red rectangle from the left-hand rule, okay? Because it's where the right side of this one is the left-hand side of the second rectangle. Okay, so I know what this area is. It's 2 times radical 2 plus 1. And this middle rectangle here is the same as the red one on the right. Okay, and so that's going to be 6, right? 3 times 2. I'll leave it as 3 times 2 so you can see the pattern. And the last one I don't know because I never went this high, right? But you can see if I put in 6 into my equation here, right into here, I'm going to get the square root of 6 plus 1 times 2. Don't forget the base is 2. So 2 times the square root of 6 plus 1. All right, so go ahead and put that in your calculator. And I'm going to do the same thing. So let's write what we have so far. So we have the integration from 0 to 6, same exact integration of the function with respect to x. It's approximately, that's really important. I'll do the first rectangle again. 2 times square root of 2 plus 1. And on the AP exam, it's always good to show the calculation. So I like to leave these like this. It doesn't really matter. If you just have the actual numbers there, even if you put a decimal answer here, as long as you go careful with 3 decimal places accuracy. And then the middle one was 6, right? Or 3 times 2, like I just said, you probably want to leave it as 3 times 2. And finally, 2 times square root of 6 plus 1. And if you threw that in a calculator, you're going to get 17.2, oh, sorry, 727, I think, 727. 17.727. Okay, and notice this is much higher. This is much higher than the actual. The actual is 15.798. Because this is a quadratic, or as you know, quadratic on its side, so it's square root, but it's quadratic in nature, these two will actually average, if not perfectly, very, very close to the actual answer. Because of the symmetry of a quadratic. In any other function, cubic function or natural log or something else, it's not going to be so close. It'll still be a good approximation, but not so close. And making n a much larger number would be much more important than what we have here. Okay, let's do midpoint. In order to do midpoint, I'm going to attempt to, anyway, delete what we have so far. I don't want to lose the graph itself. Okay, good. Because it'll be a little too messy. And like I said, the midpoint usually will be asked, you'll be asked to do the midpoint when it looks something like this, where you're skipping every other one. Now with a function like this, you could of course just put in 0.5, throw it in your calculator, and it's easy. So there's no reason, it's not difficult. It's not difficult at all to do midpoint, even if I had done rectangles of one width, okay? And on the AP exam, many, many, many times, the data is not going to be a function like this. The data is actually going to be from a table. Okay, just getting rid of some riffraff here. Okay, so let's do midpoint. And I'm going to do from 0 to 6, f of x dx. I'm just going to get this ready to go, approximately. Okay, and for the midpoint, again, the bottom of my rectangle is going to be exactly the same. It's going to be exactly the same. That's the bottom of my rectangle. But rather than going up the right side or the left side, I'm going to go up the middle. I'm going to go up the middle. Okay, and I'm going to find a point right here. And from the middle, from the midpoint, I'm going to go left and right. So you can see this is kind of nice in that it overestimates a little bit. So, right, that's... underestimates on the left, this part, I'm sorry, and then it no, overestimates on that side, excuse me, and then underestimates on this side. See, so you can see this error, particularly in something well-behaved like a square root or quadratic. This error is almost going to cancel itself out, so we're going to get a nice approximation here, even with a low sample size of 3. So that's my first one. The second one, of course, the base of the rectangle is too wide, all because of this. This is driving where I'm going with my width, so n equals 3. You'll see in one of the later formulas we do, it's 6 minus 0 divided by 3 gives you the width of each rectangle automatically. At least in this case where the data is a function, not a table, and where they're evenly spaced or sampled at every x, right? That's not always going to be the case. So for this rectangle here, we go up the middle, we hit the middle point, and then we go straight across. And then for the third, just repeat. So we go up the middle. I'm making a dotted line because I don't want you to think that that's actually a border of the rectangle, right? It's just the middle of the rectangle. So we go here, and we go across in both directions. Okay? All right, so here the area is, again, base of 2. That's always going to be the same for this n equals 3 anyway. And it goes up 2, so this is going to be 4. For this rectangle, it goes up to this point, and I need to plug in 3. That's the middle, right? We're going to plug in 3. So it's going to be the square root of 3. That's going to go right here. I'm going to plug square root of 3 in here. So I'm going to plug in square root of 3. I'm sorry, plug in 3 and get the square root of 3, right? So I'm going to get the square root of 3 plus 1, and that's going to be the height of this rectangle, okay? So it's 2 times the square root of 3 plus 1. Can't see that too well, but I think you got it. And the last rectangle is going to be, again, a width of 2 and a height of plugging 5 in. We're going to plug 5 in. That's the middle to this formula. So it's just going to be 2 times the square root of 5 plus 1. Okay, and let's add that up and see what we get, right? So again, over here, we're going to get 4 plus 2 radical 3 plus 1 plus 2 radical 5 plus 1. And put that in your calculator, and let's see what you get. And you get approximately 15.936. And if you take a look at that, that's pretty close. And again, even with a not so great, it's not a great highlight. Even with a not so great sample size here, this is pretty close to the actual answer, 15.936. Okay. All right, let's do the trapezoidal. And let's see if I can grab all this stuff again. Gently. So for the trapezoidal, what we're going to do is we're going to literally create trapezoids, as you might have thought. And you may think that you're going to get the exact same answer as the midpoint method, but you're not. Maybe you won't think that. I don't know. We're going to write 0 to 6, f of x dx. Okay, and with the trapezoidal method, it's kind of a mixture of the left-hand and right-hand rule as far as going up. We're going to go up the left side and the right side at the same time. And what we're going to do is we're going to stop both of them when they hit the function. In other words, we're not going to get a rectangle because this one's going to stop here and this one's going to stop here. And then we're going to connect the two, and I'm going to use a straight line just to emphasize something here. And we're going to connect the two and form a trapezoid. Now notice that's not the same thing as a midpoint, right? It's not the same thing as a midpoint. Midpoint, if you remember, would have been about here and across. And even though they're not totally, different value, they are definitely not the same method. Let's go to the second rectangle. So from here to, not rectangle, excuse me, but the second interval. So let's go from here to here. And we've already gone up there all we want. Now we're going to go up the right side and again, right till we hit the function. Okay, now you're going to see that the midpoint method is probably a little closer here, but again, not the same. And we're going to go probably not through that point, but it looks like it is, but not through that point exactly. And then finally, the last interval we're going to go, we've already gone up the left side, we're going to go all the way up the right side here, and we're going to make a third trapezoid. All right. Now, there's a couple ways to do this for finding the area. It is completely legitimate to simply cut off the rectangles and make triangles plus rectangles. In fact, I think a lot of times they will show that rather than the area of a trapezoid. Of course, the area of a trapezoid is just base 1 plus base 2 divided by 2. And then, of course, when you get that, times the base, right? So you got to be careful. It is a trapezoid on its side, right? Here's the parallel lines for all you geometry students. So it's a trapezoid on its side. It's a right trapezoid, of course. There's a right angle in here. And you just average the bases times the height, okay? I'm actually going to do it that way because I think it's kind of neat. But you can do the area of both of these two little sections first if you can't remember the formula or if you just want to, if you think it's easier for yourself, okay? But I'm actually going to do 1/2, and I could GCF out of 1/2 of this entire expression. In fact, we do that later. But I'm not going to. I'm just going to do 1/2 the two bases added together. And then, of course, times the height, which is 2. Or really, we're calling this the base, but it's actually the height of the trapezoid because the trapezoid is on its side, right? The trapezoid is really on its side, right? It's on its side. Okay, so this base, the first base here is easy. That's 1. Okay, and the second base is when we plugged in 2, which we did earlier, right? So that's square root of 2 plus 1. We have it over here, right? Square root of 2 plus 1. So you have to add the bases. So it's really 2 plus square root of 2, but I'm going to leave it, right? You can save yourself a little space that way because the 2 1s add up to 2, but I'll just leave it as we found it. So it's the one base plus the second base divided by 2. That's what the 1/2 is doing, and then times 2. Okay, and then repeat. And of course, you get another 1/2, and you get another big bracket like this. And then that's going to be times 2. And finally, the last one with a big bracket. Times 2. We're not going to be able to fit what it equals, but I'll find a way. Okay, so the middle one here, right, that goes on the left side. One of the bases is exactly what we just had, radical 2 plus 1. Okay, and then plus the other base. And this base is when you plug in 4. When you plug in 4, you get 3. So plus 3. And the last trapezoid is 3 plus, right, so that's 3, which is this side of the trapezoid, that one base, plus this one. And that's what we've gotten earlier too, which is radical 6 plus 1. I want to save space, which I should have. You could have put 4 plus radical 6. Okay? So add up all these together and see what you get. So if you work all that out, I think you get about 15.278. 15.278. And that also is incredibly close. Well, not close to the midpoint in this case, but pretty close to 15.798. And again, that's what that equals 3. So just in conclusion, we will have a second video on this with your homework problem, with some problems, examples you can do, and I'll solve them. But these are the 4 main methods of Riemann sums. We are going to work with a table, so this is nice. It's a function, so we're able to compare it to the actual value. But in many cases, as you'll see in the next few problems, there is no actual value, or there's no way to find the actual value because we don't have data, or we don't have an algebraic expression representing all of our data. We only have discrete data at certain points. So we'll take a look at that in the next video.